Hello everyone, my name is Renan Guarese, and I'm here today to present a work I've done with some colleagues and professors from my home university in Brazil, UFRGS. It's called a Usability Assessment of Augmented Situated Visualization. Here you can see a user interacting with an example of that, inside a classroom showing data relevant to it. So, regarding the focus area of this work, augmented situated visualization is basically a mixture between data visualization and augmented reality, where you get to see and perceive relevant information to the environment you are currently located at, particularly in a way that helps the user to identify the 3D position of each piece of data. The use case represented here is an educational example we set up, where we expose different sets of data pertaining to a classroom, specifically addressing its seats. The application is supposed to aid the person in choosing a seat that best suits their needs. The user study we've conducted tests this AR application against a 2D map of the same data in different seat choosing tasks, where participants choose seats based on different requirements given by each run of the test. The usability, choice accuracy, and steps taken for each task were measured. In this work, we used the Microsoft HoloLens to scan the real environment and display different sets of data located in the 3D world around the user, such as the temperature and Wi-Fi signal across the room. The data can be selected and interacted with via gestures in a hand-tracked virtual menu. Each piece of data displayed is related to specific chairs in the room, and they're dynamically adapted to the user position, being rotated, scaled, and having its height changed as to ease readability and avoid data occlusion. Here, we can see some examples of the data users had access to. First, a 2D map view of the room, displaying scores for each seat based on how good the airflow is. Arrows also indicate the direction and strength of the wind. In this image, the same data is displayed in AR, where users can look at the actual room and see the scores for the actual chairs in front of them. Here, these scores represent how much do people circulate in front of each seat. The intention is to help someone choose a seat where other attendees won't disturb the user by passing in front of them. The thickness of the line indicates the amount of people. Same view in augmented reality, where the red lines are projected directly onto the floor. Now onto a more complex dataset. The color-coded circles indicate which seats have any particular feature to them. For example, whether they have left-handed desks or hearing aids. Same data now in AR. The circles are replaced by cylinders, helping the users to identify the particular seats. Now, on the left side, we can see the menu users could interact with in the 2D version, which was tested in a tablet device. All of the same options and subtitles were available for users in the AR version, seen in the right side of the image, where they could gaze at the options and perform a tap gesture to select them. As for the tests performed, one at a time, users would receive an instruction to choose a seat based on a set of demands, such as seat with the highest temperature that is accessible on a wheelchair. 6 of these tasks were performed per platform for each participant, with the complexity of the demands being increased in each task. The users would go through the data either in AR or in 2D. They would then make a choice for their seat and proceed to sit on it. Both the accuracy of the choices related to the data displayed and the number of steps taken by them were measured, as well as their perceived usability of each approach with the System Usability Scale questionnaire. So, among the 16 users that were part of our test, we observed a 12.7 decrease in the number of steps for the AR solution compared to the traditional 2D map. The choice accuracy for the optimal seat was also slightly higher in AR, by around 2%. Both platforms also achieved good marks in their usability scores, even though the 2D was deemed easier to use, as expected. Regarding the main limitations of this study, we need to say that both the steps and accuracy results, although promising, did not present statistical significance. The classroom tested also was relatively small, which made it easy for users to locate the chosen seats despite the data. We also haven't yet performed tests comparing different visualization schemes within the AR paradigm. All of these points will be addressed in future works, currently being developed, where similar tests will be performed in larger and more complex environments, with more distinguished data and with a higher number of subjects. Different approaches to the AR data display and interaction will also be taken, as to find out whether an optimal method exists for each set. In conclusion, this was a preliminary work to test whether situated visualization can be helpful to users in decision-making tasks. Despite further research being needed to expose precisely where and how, we can see that it has positive effects in this sort of task. The intention is to ease the access and understanding of data to users, ultimately lowering their cognitive load while still allowing them to make good decisions. Thank you all for your attention.